So today we begin the first technical topic related directly to the course, that is equilibrium carrier concentration. Now before we begin our discussion on this topic, let me summarize what we have done so far. So far we have seen how the devices can be classified in terms of the frequency or power, okay, of their operation. Then we have seen what are the objectives of this course. Specifically we have said the objective of this course is to relate terminal characteristics to the internal parameters with the help of simple equations based on a physical understanding of all the phenomena that are taking place within the device. Then we have seen in detail what are the contents of the course. This was the first lecture. Then in the second lecture we have seen what is the uniqueness and how the technology of semiconductors has evolved. I suggest that you spend a lot of time thinking about the nature of technology and how this technology has evolved, because that part, even though it is just 1 hour, it is as important as the remaining maybe 37 hours of lecture, okay? And maybe the nature of technology itself can be discussed in a separate course and some kind of comparison be done between semiconductor technology and other technologies. Now coming to the topic, equilibrium carrier concentration. Let us see what exactly are we trying to achieve in the next 4 or 5 lectures on this topic. So the first thing is that we would like to derive a formula for explaining this particular behavior in an intrinsic or pure semiconductor. So what this graph shows is the carrier concentration as a function of temperature in a pure semiconductor. It is important to see the axis on this graph. The y-axis, that is the concentration, Ni stands for the intrinsic concentration, I is intrinsic. So the concentration axis is logarithmic, and the x-axis, which has temperature, is actually the reciprocal of temperature, okay. So if you plot the concentration, the measured value of this particular parameter on a log scale as a function of the reciprocal of temperature, then you get straight line. So this obviously gives us a clue as to what kind of formula, what is the form of the equation for concentration as a function of temperature, although we will have to determine what are the constants in this from a deeper understanding of the device physics. You can also see that the concentration is different for silicon, germanium, gallium arsenide, and this difference is quite large. So we will have to find out what is the parameter associated with the material which accounts for this difference, which is responsible for this difference. Here we have also shown the room temperature point, that is 300 K on this graph. Because the x-axis is reciprocal, you will have to convert this into the temperature so as to get a feel for what is the range of temperatures covered here. So here is the room temperature, and on this side are the lower temperatures, because it is reciprocal of temperature on the x-axis, and this side are the higher temperatures, higher than room temperature, okay. So we find in very simple, if you state very simply, that the concentration seems to vary exponentially as a function of the reciprocal of temperature, okay. That is the important information that we get. Next, what we will do is we will do a similar exercise for extrinsic semiconductors or doped semiconductors. Doped semiconductors you have two types of concentration to be considered, majority and minority, because the concentration of electrons and holes is not the same. In a pure semiconductor, the electron concentration is same as the hole concentration. So the symbol Ni in the previous slide represents electrons as well as holes, whereas in an extrinsic or doped semiconductor, the electron and hole concentration in general is not the same. So you have the majority carrier concentration, that is the concentration of carriers which is in a majority, and you also have minority carrier concentration. So you can see here again we are plotting the majority carrier concentration in an N-type semiconductor. So here this N stands for the electron concentration, this small n stands for the type of the semiconductor, that is it is an N-type semiconductor, and the 0 stands for the fact that the semiconductor is under equilibrium. We are going to discuss what equilibrium means later. So this is an equilibrium concentration of electrons in an N-type semiconductor, and this is also the majority carrier concentration because electrons are in a majority in an N-type semiconductor. So this concentration is plotted again on a log scale as a function of temperature, reciprocal of temperature on the x-axis. You have an additional parameter here as compared to the previous graph, and that is the impurity concentration or the doping. So whereas you had only one, line for a material in the previous graph, here you have a number of lines. This is for silicon. What we are plotting here is for silicon. We have a number of lines, each for a different doping. So here what is shown is doping level of 10 power 15, 1 into 10 power 15, 5 into 10 power 15, and 1 into 10 power 16. So doping is a parameter on which the concentration will depend. And room temperature is shown here. So the room temperature is close to the left end here in this particular graph. So the concentration has been shown for less than room temperature as well as for more than room temperature. You find that there is a small region from this point here to somewhere here over which the concentration is constant as a function of temperature. This is the region in which the devices operate. This range over which the concentration is constant varies with the doping, and this range is wider for higher doping levels. Generally, this range is referred to as the extrinsic range. So we will have to explain this behavior. How do you get a constant concentration of majority carriers over a certain temperature range, and how do you get straight lines when you plot log of concentration with reciprocal of temperature on the extremes of this range. So that is for low temperatures here and for high temperatures here. That is what we would like to explain. So next, minority carrier concentration in an extrinsic semiconductor. The minority carrier concentration we will have to show is given by the intrinsic carrier concentration square divided by majority carrier concentration. So first slide that we showed was intrinsic concentration, next slide was majority carrier concentration. So if you square the intrinsic concentration divide by the majority carrier concentration, then you will get the minority carrier concentration. So for example, in an N-type semiconductor, the hole concentration is a minority concentration. So PN0, P is the hole concentration, suffix N is the N-type semiconductor, and suffix 0 represents equilibrium. So equilibrium concentration of holes in an N-type semiconductor, which is also the minority carrier concentration, is given by Ni square divided by N suffix N 0. In other words, in general we will show that under equilibrium conditions the whole concentration into electron concentration, the product, is equal to square of intrinsic concentration. P naught n naught is Ni square. Now to explain these things, let us see what are the topics that we will cover. So first we will review some basic concepts such as types of semiconductors, the difference between the thermal equilibrium condition and steady state, the wave particle duality. Then we will go to the intrinsic semiconductor, for which we will consider the bond and the band models, generation and recombination. We will see the concept of the hole, that is a positively charged carrier. Then what is the idea of an effective mass of a carrier. Then we move on to the extrinsic semiconductor or doped semiconductor, wherein we will discuss majority and minority carriers, the bond and band models of the extrinsic semiconductor, Fermi-Dirac statistics and Fermi level. So let us begin with the first topic, and that is classification of semiconductors. It is important to state right at the outset that we are considering concentration in the semiconductor bulk. Supposing this is the semiconductor block, this is the bulk, and this outline is the interface. Now strictly speaking, a small region near the interface is to be excluded from the bulk, because this region will be affected by the properties of the surface or the interface. So it turns out that the interface is as important as the bulk. So very often when we draw a diagram like this, we tend to concentrate on the bulk because the area is large, whereas it turns out the interface is a very important part of the semiconductor. In fact, the understanding of the surface is still not clear. You have a journal devoted to just the science of surfaces that will give you an idea of how complicated the surface is. Now having said that we are talking about the semiconductor bulk and the concentration there, let us see what are the types of semiconductors. So one classification is simple and compound. Example of simple semiconductor is silicon, germanium, etc. These semiconductors, you have just one type of atoms regularly repeated. Okay. On the other hand, in compound semiconductors, you have atoms of more than one element, okay, constituting the semiconductor. So simple semiconductors are also called elemental semiconductors because you have only one element present. Example of compound semiconductors, for example, gallium arsenide, indium phosphide. You can also have more than two, for example, gallium, indium arsenide, and so on. You can even have 4 elements present. Now another classification of semiconductors is pure, intrinsic and extrinsic semiconductors. Pure semiconductor is a semiconductor which has no impurities or no defects. This is important. that is, it is a perfect crystalline material. There is a regular arrangement of atoms. So let us say I take silicon. In this course, unless otherwise stated, the element that we are going to consider is silicon. So let us take silicon. A pure silicon piece, a pure crystalline silicon, would mean just a regular arrangement of silicon atoms without any disruption. Now one must understand that this statement is valid only for bulk, because when you, even if you take pure silicon crystal, as you move to the interface, there is a disruption in the periodicity, because you do not have any silicon atoms beyond the interface. So within the bulk this is valid. So when we are talking of pure semiconductor, strictly it means that we are talking of this region where there are no defects. A defect is a disruption in the regular arrangement, or no impurities, no atoms other than silicon present. Such a semiconductor is impossible to get. Okay, so where the semiconductor materials which are used in semiconductor devices are 99.9999% pure, but still there is some impurity. It is very difficult to make a very pure crystal. That is why we introduce a concept of intrinsic semiconductor. The intrinsic semiconductor is one which may not be totally pure. It may not be totally pure. There may be some defects. There may be some small amount of impurities, but the concentration of electrons and holes in this semiconductor would be the same as that in a pure semiconductor. This is possible. When is it possible? When the effect of one type of impurities compensates the other impurities. So impurities are present or defects are present, but they are compensating each other, so that the concentration in this semiconductor remains the same as in a pure semiconductor. Okay, so intrinsic semiconductor. And extrinsic semiconductor is anything that is not intrinsic, which means it is a semiconductor with defects and impurities present. Okay, and wherein the concentration of holes and electrons will not be the same under equilibrium conditions. So that is an extrinsic semiconductor. So doped semiconductor is definitely an extrinsic semiconductor unless the doping is of two types of impurities which are exactly compensating each other, in which case it will become a intrinsic semiconductor. So pure semiconductor means no defects. Or impurities. Intrinsic may contain defects and impurities, but concentration same as that in pure semiconductor. Extrinsic, defects and impurities are present. Under equilibrium conditions, electron and hole concentrations are not the same. So it is obvious that extrinsic semiconductor is more complex than intrinsic. So you need to proceed in a progressive fashion from simple to difficult. So that is why we will start with first the intrinsic semiconductor and then go to the extrinsic semiconductor. Next, let us discuss the idea of the thermal equilibrium or thermodynamic equilibrium. So many times the word thermodynamic is replaced by thermal equilibrium. Thermal, the word thermal. If you go into nitty-gritties of the issue, thermodynamic is not exactly the same as thermal. Okay, but for our practical purposes, we will assume that the two words are interchangeable. What is the meaning of thermal equilibrium, and why is it that this concept is important in modeling or analysis of devices? It turns out that in physics there is a general philosophy that is followed for modeling complex situations, and that is that you treat a complex situation as a small deviation from a idealized situation which can be treated mathematically. This is a very important idea commonly followed in physics. A complex situation let me introduce the word real life. Can be approximated as a small deviation from convenient idealized condition which is amenable for amenable to mathematical treatment. And one must always add the word simple here. Actually, this is not something unusual. See, for example, supposing you want to tell the location of some place to a person who doesn't know the place. Okay, very often you tell a landmark and you say it is about so many meters or right so many feet from this place. Okay, you tell a landmark. You don't tell the person how far is that place from place where your place of reference where you are. Okay, so this is the idea here. So we are talking of a complex situation. Find out if there is an idealized situation, that is, it may not be real situation, okay, which is very near to that. And then if you have a model for that ideal situation, then you can introduce a small disturbance and then try to model the complex situation. Once you understand this philosophy, then you will understand this idea of thermal equilibrium. The thermal equilibrium is a convenient idealized condition. It is not achievable in practice, very difficult to achieve in practice, okay, but it is a convenient idealized situation. Many phenomena that we encounter can be modeled as deviations from thermal equilibrium, okay, small deviations from thermal equilibrium. That is why many times you will find the word quasi-equilibrium attached to the device analysis or modeling. It is a quasi-equilibrium model. What does it mean? You are treating it as a small deviation from equilibrium condition. So what is the definition of thermal equilibrium? A piece of semiconductor is said to be in equilibrium with its environment. Whenever you talk of equilibrium, you must talk of two entities. The equilibrium is between two entities, okay. So it is understood when you say a semiconductor is in equilibrium, in brackets it is in equilibrium with its environment, okay. So many times this in equilibrium with the environment, the with the environment phrase is deleted, that is understood. So a semiconductor is said to be in thermal equilibrium with its environment if for any process that may be going on between the semiconductor and the environment, there is an inverse process going on at the same rate. This also applies for processes within the semiconductor. For any process that is going on, or for every process that is going on, there is an inverse process going on at the same rate. It is a very simple statement of thermal equilibrium. It is also called the principle of detailed balance. Both the words are important here, detailed and balance. So the word balance is what is indicated here by these two arrows, these two pairs of arrows. So there is, for every process that is going on, there is an inverse process going on at the same rate. That is the balance aspect of it. Now what is the meaning of the word detailed balance? Detailed balance. The detailed balance means that you look at the process in as much detail as you want, and at every level of detail this balance will hold. This is a rather stringent condition. So what does it mean? It means, for example, supposing there are 10 particles moving from say point 1 to point 2. There are 10 particles moving from point 1 to point 2 at a certain rate. Then exactly 10 particles of the same type will be moving from point 2 to point 1. Okay? So if there are 10 electrons moving from 1 to 2 in a given time, in that amount of time exactly 10 electrons will be moving from 2 to 1. Not only that, if all the 10 electrons are not of the same energy, 2 electrons have energy E1, 3 electrons have energy E2, and so on. There is a distribution of energy. The electrons are distributed over energy. Then exactly 2 electrons of energy E1 will be moving from 2 to 1. Exactly 3 electrons of energy E2 will be moving from 2 to 1. This is the meaning of detailed balance. So you go on looking at the process in more and more detail. At every level of detail the balance is maintained. That is the meaning of the detailed balance. So the principle of detailed balance, it says that for every process there is an inverse process going on at the same rate. Okay? So that is the meaning of thermal equilibrium. Now even though this statement is short, pithy, and if you take the words literally it is not very difficult to understand, but its implications many times are not so clear. Okay? So we can use a more practical definition that which will be more verbose than this, but which we will understand clearly. Okay? So in which we state conditions 1, 2 and 3. You just say, is this condition valid? Yes. Is this condition valid? Yes. Is this valid? Yes. Okay, then it is in thermal equilibrium. Okay? So such a definition of thermal equilibrium would be as follows. So a semiconductor is in thermal equilibrium if one, no external excitation other than temperature. Two, no net motion of charge or energy. If these two conditions are valid, then the semiconductor is in equilibrium. So to understand this idea, let us look at some simple examples of non-equilibrium conditions. Okay? We must illustrate this with examples. So you can give examples of, because as I said, equilibrium is very difficult to achieve. So let us see what is meant by non-equilibrium. Then you can by inference understand what would equilibrium mean. Okay? So let us see, one example is, supposing you have a semiconductor. One end you have a temperature T1, other end you have temperature T2. Okay? Now the first condition is satisfied here. There is no excitation other than temperature. That is true. However, if this temperature is more than this temperature, then there is a flow of heat from T1 to, let us assume T1 more than T2. Then there is a flow of heat from this end to the other end. That is flow of energy. And there is no inverse flow of energy to balance this. It is a one directed process from T1 to T2. So it is not under equilibrium. Of course there can be motion of charge also, but we need not go to another condition, because one condition is violated, it is not under equilibrium. Let us take another example. Supposing you have light falling on a semiconductor. okay, light falling on a semiconductor. It may falling on all sides or maybe one side, does not matter. This semiconductor is not under equilibrium because you have light shining on the semiconductor, photons are being absorbed and then that energy is being converted into another form of energy. There is no inverse process, right? It is not as though semiconductor is giving out light, okay. That is interesting, which means that if a semiconductor is visible, it is not under equilibrium, okay. So semiconductor should be under dark conditions. So this is the implication of equilibrium, we must understand. Let us take another example, which of course is more straightforward. Supposing you have a semiconductor and you apply an electric field so that current is flowing. Now it is obviously not under equilibrium because first of all the first condition itself is not satisfied, okay. There is excitation other than temperature, okay. So this is how you can find out whether the semiconductor is equilibrium or not, okay. So a semiconductor will be in equilibrium if it is not visible, it is under dark conditions and there is no excitation of electric field or any other such energy, okay. So these are non-equilibrium examples of non-equilibrium conditions. Now semiconductor devices are only useful under non-equilibrium conditions. You can't get anything out of a device if it is under equilibrium, okay. So as we said right in the beginning that the thermal equilibrium is a convenient idealized situation because many practical situations can be treated as small deviations from this situation, okay. In other words, many practical situations can be treated as quasi equilibrium situations. Let us understand why. Why is it that many situations can be treated as quasi equilibrium situations, okay. We will take an example. Let us take a PN junction, okay. What I am trying to tell you, you must accept as facts because we have not done an analysis of a PN junction, okay. So you just accept as a piece of information. Across the junction in a PN junction you have a very large current density even under equilibrium conditions for electrons as well as holes. But what is important is that current density in one direction is exactly balanced by current density in the other direction. In other words, the thermal equilibrium is not a static equilibrium. This is very important. The thermal equilibrium is not a static equilibrium. It is a dynamic equilibrium. There is intense activity under thermal equilibrium. Only thing is the activity does not contribute anything in any one direction. That is what is important, okay. That is why we said no net motion of charge or energy. It does not say no motion of charge and energy. This is very important. No net motion, the word net is very important, okay. So it is a very dynamic situation in which there is intense activity but which is not in any one direction, okay. This is the reason why this condition is useful starting point, because now if you add any other excitations then we can treat this condition as a small deviation from equilibrium condition. So let us take this example. For example, for a PN junction one can show, if you take for electrons at the junction there is a current of 1000 ampere per centimeter square. So there is one tendency for electrons to go from p to n at the rate of 1000 ampere per centimeter square, that is density, and it is exactly balanced by another tendency. As we will see, one tendency is the drift, another tendency is the diffusion. Okay, we will not get into more details here. All that I want to point out is that is the current density under equilibrium conditions across the junction, but there is no net effect of this because the net current is 0. Obviously you can't get a current out of a PN junction if it is under equilibrium. Okay, now you will appreciate how a practical situation can be treated as a small deviation. Let us take the current levels encountered in a diode under practical conditions. Okay, so here again I will not make a calculation. You can make a calculation, you can take a practical device, what is its area, what is the current level that you are going to have, okay, and then you can find out the current divided by area as the current density. That exercise I will not do, right, because for this we must get into the structure of the diode and so on, but you can, that will result in some kind of a number like this, say 10 ampere per centimeter square, a practical current. On applying voltage, I is 10 ampere per centimeter square. So this is equilibrium condition. If I were to show after application of voltage, obviously this is valid only for some voltage that is applied, okay, but I am just taking one example, practical example. So that is I. So in other words, now what has happened? Obviously this is not exactly balanced by that. Okay, one tendency is slightly increased, another is slightly reduced, or maybe one is not affected, the other is affected. That is also possible. The net effect is that, so I will show it here, this arrow I am showing it longer and this arrow I show it shorter to show that an imbalance has been created there of 10 ampere per centimeter square. Now how can I get 10 amperes from 1000 amperes? One way I can get is 1000 becomes 995 in one direction and it becomes 1005 in the other direction, right. So I can have maybe 1005 in this direction and 995 in other direction. So the difference is going to give me 10 ampere per centimeter square. Now you can see that this is really a small deviation from equilibrium. 1005 is very small deviation from equilibrium, right, 5 out of 1000 is a very small percentage change. Okay, so this is why the thermal equilibrium condition is important. It is a dynamic condition, it is a condition of intense activity, okay, and in practical conditions the deviation from equilibrium is very small. Let us distinguish the equilibrium condition from steady state. Many times people confuse between equilibrium and steady state, so it is important to distinguish between the two. Steady state means all processes are constant as a function of time. All processes are constant as a function of time. It is not necessary that for every process there should be an inverse process. That is equilibrium. Okay, steady state means all processes are constant as a function of time. So if you want to show the relationship between equilibrium and steady state, it would be something like this. You can use a Venn diagram. If this shows steady state, then that is equilibrium. So EQ stands for equilibrium. So if a semiconductor is in steady state, then okay, is it under equilibrium? This clearly shows that if a semiconductor is in steady state, it need not necessarily be under equilibrium. but if a semiconductor is under equilibrium, it is definitely under steady state. Okay. But the importance of steady state is similar to importance of equilibrium. Many dynamic conditions, that is non-steady state conditions, where parameters vary as a function of time, can be treated as small deviations from steady state condition. That is why you will find for transient analysis they will attach a phrase called quasi steady state analysis or quasi static analysis. So transient conditions can be approximated as quasi steady state or quasi static conditions. The word quasi always means small deviation from. Okay, so now it's time for some discussions or questions.
Sir, can you please clarify the notation N0?
Let us look at this slide. What you are talking about is what is this N0? Now in this notation, this N stands for electron concentration. This N stands for type of the semiconductor, that is N type. As you know, an N type semiconductor is one in which electrons are in a majority. This suffix 0 stands for the fact that the semiconductor is under equilibrium. So N suffix N0 means the electron concentration in an N-type semiconductor under equilibrium conditions. So as per this notation, if I write PN0, that would imply the whole concentration in an N-type semiconductor under equilibrium.
Sir, I have a question regarding the majority carrier concentration versus temperature behavior. You said that for higher doping, the extrinsic range is wider, but the figure shows a wider extrinsic range for lower doping. Why?
Let us look at the slide again. This is a good question. What you want to know is that, let us look at the green line here. It has a constant portion. This range of the constant portion for the green line appears to be wider than the constant portion of the, let us say, the red line, and also the constant portion of the blue line here. So this gives an impression that for Nd equal to 1 into 10 power 15 per centimeter cube, the extrinsic range is wider than the extrinsic range of 5 into 10 power 15 per centimeter cube and 1 into 10 power 16 per centimeter cube. This is happening because there is some amount of distortion when you plot the concentration as a function of reciprocal of temperature rather than as a function of temperature. So let me explain to you this in detail. On the reciprocal of temperature axis, higher and higher temperatures tend to get compressed more and more. For example, here this temperature corresponds to about, say, 600 K, whereas the 0 of this temperature axis, reciprocal of temperature axis, corresponds to infinite temperature. So 600 K to infinite temperatures are compressed in this small region. That is why you are not able to see the difference between the temperature, this corner of this green curve, and the temperature corresponding to this corner of the red curve, whereas there is a significant difference in these two temperatures. On the other hand, you are able to see the temperature difference between this point which is one end of the flat portion of the curve, and this point which is also the end of the flat portion of the green curve. So this point, the temperature difference between this point and this point is very visible. This is because these are lower temperatures. On the reciprocal of temperature axis, their difference is enhanced as compared to the higher temperatures, and that is why you feel that the higher doping levels have lower extrinsic range than lower doping levels.
Why should equilibrium condition imply steady state? For example, there is a process whose rate increases with time, and this process can be exactly balanced by an inverse process whose rate also increases with time. Is this not a case of non-steady state equilibrium condition?
It's a good question. Let me explain to you with an example. Let us say this is a semiconductor, and in this, between some 2 points, there is a process of electron transfer from one point to other point in this direction at some rate. Let us say 10 electrons per second, and you have an exactly inverse process going on between the same points, and you have a reverse transfer of 10 electrons per second. Now what you are saying is, if as a function of time the rate goes on increasing, that is maybe after a minute or so this 10 becomes 12, and this 10 here reverse process also becomes 12, and then maybe after another minute it becomes 14, and this also becomes 14, then is it not a case of equilibrium? It is obviously not, and what you are saying is it is not a case of steady state, because the processes are not constant as a function of time. This process is increasing from 10 electrons per second to 14 electrons per second. Now the catch here is that we have said in the definition of equilibrium that for every process there should be an inverse process going on at the same rate. Now if the rate of electron transfer from point 1 to point 2 is increasing from 10 to 14, then it means that the number of electrons in this region is increasing from 10 to 14. More electrons are coming in from somewhere else, because otherwise the electrons involved in this exchange cannot go on increasing. So the number of electrons are going on increasing as a function of time within this region. Somehow more electrons are coming in from somewhere, maybe from outside or maybe from inside the semiconductor, from some other place electrons are coming to this point as well as to other point. Now there is no reverse process for this particular process. So there is a net movement of electrons from this point to point 1 and some other point to point 2, and there is no corresponding inverse process. So that is why this is not a case of equilibrium.
Sir, is silicon a pure or intrinsic semiconductor?
Let us look at the classification of semiconductors once more. We can divide the semiconductor types into simple and compound. So simple semiconductor is also an elemental semiconductor. Example of simple semiconductor we said is silicon. Example of compound semiconductor is gallium arsenide. Now a simple semiconductor can be either pure or it could be intrinsic or it could be extrinsic. Similarly, the compound semiconductor also can be either pure or intrinsic or extrinsic. So, a semiconductor is either simple or compound, and a simple semiconductor can have any of these three types, and a compound semiconductor can also have any of these three types. So, your question that whether silicon is pure or intrinsic semiconductor does not make sense. That is, a silicon can be either pure or it can be intrinsic or it could be extrinsic. If there are no more questions, before leaving this lecture, I would like to come back to this particular slide of majority carrier concentration in extrinsic semiconductor, related to which a student had a question about why the extrinsic range is smaller for higher doping levels as drawn in the diagram, whereas in practice the extrinsic range should be larger for higher doping levels. This thing we are going to examine later, but one point that I did not discuss and which the students may like to know is that if, because of choice of a reciprocal of temperature axis here, a wider extrinsic range appears as a smaller extrinsic range, and if such distortions are taking place, then why should we choose a reciprocal of temperature axis at all? This is a very relevant question, and this has to do with how experimental data needs to be plotted in order to confirm a model. If you plot the same graph using a linear temperature axis instead of the reciprocal temperature axis, then these two ends, that is this portion of the graph and this portion of the graph, would not be linear and they would be non-linear. There are some advantages in getting straight line portions in a graph, because then the data and the model can be very easily checked. This particular aspect is very important in checking of the models. So we normally like to plot the data in such a way that its various regions would be straight line or close to a straight line, because it is very easy to fit a straight line to a set of points. So from the point of view of checking experimental data, whether it fits into a model, it is good to choose a axis in such a way that you get straight lines, but you must be aware of the distortions that might take place, and therefore you must also know how the same data looks when you choose linear axis for both the variables. Now this particular point I will discuss in greater detail when I take up the model corresponding to majority carrier concentration in extrinsic temperature, majority carrier concentration in extrinsic semiconductor as a function of temperature. So when you write down the equations, and then it will become clear why we choose a logarithmic scale for concentration and a reciprocal of temperature scale on the x-axis.